In this video, we're going to take a look at a network analysis problem. We will analyze a network made up of branches and junctions, where each junction yields a linear equation and the total flow into a junction is equal to the total flow out. Let's set up an example that has 5 junctions. We'll label them 1, 2, 3, 4, and 5. Now we'll show their connections. And we'll create these arrows which show the direction of the network flow. Next, we'll label our branches. Here's x1 and x2. We'll call this one x3, x4, and here we have x5. For our remaining 3 branches, we'll provide integer values. So recall, this would be a junction, and all of our circles here represent junctions, and this would be an example of a branch. And these connecting lines between our junctions represent branches. We also want to recall that the total flow into a junction is equal to the total flow out. So for example, here we see that 20 is flowing into junction 1, so we know that between x1 and x2, the outflow, together the sum of x1 and x2 must also equal 20. What we're going to do is analyze the network and create a system of linear equations that represents the network. Here we've recreated our network from the previous page. Starting with junction 1, I can see that x1 plus x2 is equal to 20. Since I know that the total flow in equals the total flow out, the sum of x1 plus x2 is equal to 20. Now let's look at junction 2. Note that at junction 2, the direction of the arrows in our variables are going in 2 opposite directions. So here we have a difference. We have x3 minus x4 equals 20. And actually that equals negative 20. So let me rewrite this to add a negative sign here. Looking at junction 3, we have x2 plus x3 equals 20, where x2 and x3 are both flowing into junction 3, and our two branches flowing outward sum to 20. For junction 4, we have x1 flowing in, and then x5 is flowing out, so that's minus x5 equals, and then since 10 is flowing inward into the junction, that's negative 10. Finally, for junction 5, we have negative x4, since x4 is flowing out of junction 5, plus x5, which is flowing into junction 5, equals negative 10, since 10 is flowing into junction 5. Here I've copied our work from the previous screen. Now we'll set up an augmented matrix. For junction 1, we have 1, 1, 0, 0, 0, and 20. For junction 2, we have 0, 0, 1, negative 1, 0, and negative 20. For junction 3, we have 0, 1, 1, 0, 0, 20. For junction 4, we have 1, 0, 0, 0, negative 1, and negative 10. And then for junction 5, we have 0, 0, 0, negative 1, 1, and negative 10. And note that the 1s and 0s simply represent our values for x. In other words, where I have 1, that represents a variable with a coefficient of 1. Where I have a 0, that means that the variable is not present in that particular linear equation. So there's x1, x2, x3, our x4s, x5s. Once we've written out our augmented matrix, we can put this into a graphing calculator in order to quickly convert it to to row echelon form. If you're using a TI-83 or TI-84 graphing calculator, you'll access your matrix and set it up as follows. You'll type second matrix, then you'll arrow right to the edit key. Next, you have to assign the size of the matrix. In this case, our matrix has 5 rows and 6 columns, so we'll call it a 5 by 6 matrix. Once you indicate that you're using a 5 by 6 matrix, you'll enter your values in row by row. Then you'll type second quit. Then you'll type second matrix again, and this time you'll use the arrow key to highlight the math category. From here, you'll scroll through your list and select REF, which stands for row echelon form. Next, you'll press enter to select row echelon form, and then second matrix, and if you used matrix A, you'll highlight matrix A and press enter. Once you select matrix A, or whatever matrix you were using, press enter, and you should get the result, which I'll write on the following screen. For row echelon form, you should have Now here, we see that we have lead coefficients for x1, x2, x3, x4. And note that for x5 we have a 0, so we're going to let t equal x5. So if x5 equals t, then we have x1 minus t equals -10, x2 plus t equals 30, x3 minus t equals -10, and x4 minus t equals 10, where x5 is equal to t. Rewriting these equations, we have x1 equals -10 plus t, x2 equals 30 minus t, x3 equals -10 plus t, x4 equals 10 plus t, x5 equals t, where t is a real number. Therefore, the analysis of this particular network, shown here, indicates that the system associated with the network has an infinite number of solutions. This concludes our example. I hope you found it helpful, and we'll see you next time.